So Venn diagrams are a notation to reason about the sets. So how do they work? You have a square box, this represents the universe, and then a set is a bubble inside. And so when you want to discuss the things, you put, for example, intersection, union, and so on, you put the two bubbles, and you create regions. If you have two sets, how many regions you have? 2 to the n, you see them there, right? Here you have the two bubbles, and you have the 4 regions. And these regions has a meaning. So, what is the red? Yes?
Intersection.
The intersection, because if you point there, this is in one bubble and is in the other. What is the other one? Union. Could you say what is the difference?
What is the difference? The reference.
Yes, I didn't put it there. So if we have these two sets, the difference between A and B, let's say that the first one is A and the second is B, or the other way around, it doesn't really matter.
So the difference here is the half moon.
Right, it's the half moon. It's the half moon. All right? The difference is the half moon. And you can find then, this works well when you have two sets. Works somehow when you have 3 sets. If you have 4 sets and you want to consider everything, now you have 16 regions. It gets very messy. If you go on Wikipedia, you see that and these regions are no longer bubbles. They have pieces that hang out to consider all the cases. It is not so convenient to reason anymore. So Venn diagrams, useful to reason. So there are some elegant formulas about all this stuff. This one means that this is associative. You see the parentheses? Here, first you do the union of B and C, and then you do the union with A. But in this case, first you do the union of A and B, and then you do the union with C. And so we call this associative. This works also when A, B, and C are numbers, and the union is, for example, addition. Works as well. This was also with Booleans when this one is odd. Alright, this is commutative. That means that if you do the union of A and B, this is the same thing as doing the union of B and A. And again, this works for Booleans with the appropriate connective. This works for numbers with the appropriate operation. Then there are things which are specific of sets. Let's read this one. A union A intersection B is A. How would you reason about this?
You take the chunk that's in both A
Right, you would reason with the Venn diagram, right?
and then
So let's draw it, and then you tell me what are the various parts. So if I do a Venn diagram to reason about this, I will have this one, and this will be A, and this will be B. Let me put it here, A and B, so we know which is which. And here, what I'm saying in this formula is that A union, the intersection of A and B is equal A. All right? So first, let's look at A, and I make it red, right? This is A. Now, now I do the intersection of A and B, and I make it blue. And now what do? I put the two together, right? Do you see that this is A?
Yes.
Yes. All right, and so Venn diagram were useful here to reason about this. Good. And so there are dozens more. Some are in the textbook. So union and intersection can be generalized to more than two operands, exactly like addition and multiplication can be generalized to more than two operands. In fact, later on, instead of having A1 union A2, A1 and 2 and so on will be numbered, and instead of the union we have a plus, and we will reason about this. And so here we have a notation. How do we read that one? Union for n, small n, that goes from 1 to big N of A sub n is equal to that is there. You do A1, union A2, union A3, up to A big N. And there is a definition, right? And this is the set of X such that X is in some A sub n. For some n, X is there. We have a very similar formula for intersection. In some cases, we may consider an infinite number. So big N will be infinity. And of course, we don't write this one here. With infinity, we write with a dot and stop there. So far so good? This is just notation. There is not much to understand here. All right, partition. What is a partition of a set S? We partition S a intuitive idea as if this is your set, you take a pair of scissors and you cut it into pieces. First you cut this one, then 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 you cut this one. You see the various pieces with scissors? When you cut it, an element of the set either goes on one or goes in the other, right? So the intersection of all the species is empty. There is no point that is in two pieces, right? When you put all the pieces together, you get back the set. And so this is a partition. Of course, there are many partitions, right? If my set S is 1, 2, 3, and 4, who can tell me what is a partition? 1 and 2, 3 and 4. This is a partition, right? This is like my set is here, and here I have 1, here 2, here 3, and here 4, and I just cut it in this way. Right? I could cut it more. How could I cut it more? I also cut this one here. And then another partition would be still 1, 2, but now here I have 3, and here I have a 4. Yes? All right, this is another partition. So there are many partitions. Say it again? Right, so if we look at the definition, says that all these elements that we put in the partition cannot be empty. So here I cannot put the empty set there. And when I put all the subsets together, I get back the original set. Yes?
Can you make a partition of a set and the empty set?
No, you don't want a very empty set. However, what you raise is interesting because it's an extreme case. If this is S, a partition of S is the set that contains S. So here I don't make any cut. I have set without making any cut. I put it in the partition. This is perfect because that is not empty. And when I do the union of everything, I get back the original set. Here, there is only one. It's already the original set. Yes? Can you?
Infinitely do that?
Infinitely do what?
Make a set. Or a partition.
Right, but typically we don't. we will see at some point a very interesting algorithm that uses partition at the very end of this class. So what is a partition? We have a set, we take a subset such that every subset is not empty. And when we put all the subsets together, we get a set. The set of these subsets is called a partition. So if you have a set with n elements, how many elements can it be in a partition? What is the biggest number and the smallest number? N is the biggest number, right? This is the case in which each subset is just one element. Very good. And the smallest number? 1, the entire subset. Fantastic. Good. Alright, so with this one, I finish this discrete structure that we call set. How long I have? What time does the class end? 1:20. All right.
It's been so long.
Exhausting. All right. We'll start to catch up a little today. All right, so we saw this data structure again, right? Should I summarize a little bit before we move to the next? All right. This is structure. What is the idea? The idea is that of a container. In this container we put elements, and we call it the set of these elements. Crucial operation, membership. We take one element and one set, and we tell whether this element is in the set. Answer is yes or no. This is the crucial operation. Almost everything else comes from this one. Which operation we make? Subset. A is a subset of B if every element of A is an element of B. Subset. Equality. Two sets are equal if every element of A is an element of B and every element of B is an element of A. Which is equivalent to say A is a subset of B and B is a subset of A. Someone pointed out before that when we consider this one, we also have the reverse. So we can write A subset of B, yes, thank you, or B subset of A of or A superset of B or B superset of A.
Could we also say that A is a partition of B, B is a partition of A?
No, these are very different concepts. So when we do subset or superset, we have two sets. When we do partition, we have one set only. So this is equivalent to what? For numbers, A less than B or B less than A and A greater than B or B greater than A. Right? And of course, here we can put an equal, like here we put an equal, right? Can or cannot. All right, we have this operation. We talk about the power set. The power set of a set A contains all and only the subsets of A. All of them. We spent a bit of time discussing combination of sets, union, intersection, difference, and so on. Interestingly enough, when we define these, we use a formula of this kind that this is a Boolean, right? We learned this about Booleans. So Booleans help us, we use them in order to define operations on sets. We look at Venn diagrams, some properties, and partitions. All right, not much stuff. I want to finish this one, then look at the homework just to see that the exercises of the homework, the problems of the homework, cover some of these aspects. Of course, it can't cover everything, but they are there. Another structure, Cartesian product. We write it in this way, A cross B. This is the Cartesian product of two sets A and B. And how is this defined? A cross B is the set of pairs where the first element is in A and the second is in B. This notation is the notation for a pair. So it's just definition. Any idea why we use this one? This is as elegant as the power set. The cardinality of the Cartesian product of A and B is what? Cardinality of A times the cardinality of B. Sometimes we don't write the times, we just write A, B. But sometimes we put the cross to denote multiplication. Should we make an example? If A is 1, 2, 3, and B is alpha and beta, what is A cross B? What are the elements of this one? The pair 1 alpha, 2 alpha, 3 alpha, 1 beta, and so on. All right, and if you count them, how many will they be? 6. And why 6?
3 times
3 times 2. Very good. All right. We use a power notation for this, where if we do the Cartesian product of only one set with itself many times, n times, we write it A to the n, where the definition is there. So if I continue my example, where A was 1, 2, 3, and I consider A cubed, who can tell me an element there? Yes, this is probably not the best example, so I'll ask you another one. 1, 1, 1. Right? Let me write it. I mean, this is very simple. A is 1, 2, and 3. And I want A cube, which is what? A cross A cross A. And so, this is defined a set of triple x, y, z, such that x is in A, y is in A, and z is in A. Yeah? And so 1, 1, 1 is there. Also 1, 2, 3 that someone said is in there. Also 3, 3, 3 is in there.
And 2, 2, 2.
2, 2, 2 and 3, 2, 1. How many elements there will be there? So here we have that the cardinality of A to the n is equal to what? The cardinality of A to the n. Right? It's kind of elegant. So what is A to the 1? the one will be x such that x is in A, right? And so putting between parentheses or not doesn't change very much. Doesn't change very much. Can we have A to the 0? Yeah, by stretching it a little bit. What will be A to the 0? A to the 0 will be what? Open close parenthesis, right? By stretching the definition. So there are some programming languages that have this. Some programming languages have tuples. And the programming languages that have tuples have a type that is called unit. And this unit type has only one element, which is open close parenthesis, which is called unit as well. So the type and the element have the same name. On the one hand, may be confusing. On the other one, you have to remember only one. And there is only one element in that type, so it's kind of natural. All right, one more structure. This is a multiset. First, let me make an observation. If you have a set, in the set, an element is either there or not. You cannot have a count how many times the element is in the set. There is no operation that is able to see that. Membership just says yes or no. And so we say that there are no repetitions because even if you repeated the element, nothing changed. In a set, there is no order. If you have a set with the elements 1, 2, 3, this is exactly the same as the set with element 3 to 1. There is no order. So now we have another structure that we call multiset. A multiset is like a set in which the element can be repeated. That's the set. Still, there is no order of the element, but the elements can be repeated. And now let's look a little bit what's going to happen. Yes?
So sets are not ordered, are tuples ordered?
Yes, sir. Tuples, every slot. In fact, if you look at the example that I did with 1 and alpha, you have 1 alpha, you don't have alpha 1. You could have the Cartesian product B cross A, which is obviously different than A cross B. Yes?
But it doesn't matter what order you write the tuple. So like
No. Now, give me a second and we get there. All right. So in a multiset, this operation membership, how does it change to make sense of this? Now you are inventing or you are creating math. I just help you a little. In a set, you have a membership. You take one element and one set, and it says yes, no. In a multiset, what this operation is supposed to do?
should tell you how many of that.
Fantastic. I should tell you how many times that element is in the set. So if it is a 0, means that the element is not in the set. And if this 7 means that in that multiset, there are 7 times, 7 copies of this element. All right? Very good. It makes sense. Now, what about union and intersection? First, let me make an observation. This author in this textbook represents sets and multisets in the same way. So, when we write something, I have to tell you whether it is a set or a multiset. Because by looking at it, you don't know. All right? Some authors use a different notation. So, by just looking at it, you know whether it is a set or a multiset. And so here now I'm talking about multiset. If I have this one, 1, 1, 2, let me say, yes, union, 2, 3, 2. The order doesn't matter. What are the elements of this as multisets? All right, if you do the union, there are two options here, right? That make sense. The first one is 1, 1, 2, 2, and 3. The other option is 1, 1, 2, 2, 2, and 3. Both make a kind of sense, right? Which do you think is more interesting? First, both exist. So there are several flavors of multisets where you could have the both. But one makes more sense than the other. Yes?
Should it be the first one so that if you do the union of the set with itself, it doesn't change the set?
Fantastic. So the one that makes more sense is the first. And why is this one? Because the idea is that if you make the union of the set with itself, you should get the set itself. And if you do the intersection, you should get the same. So union and intersection for sets and multisets becomes very similar. And so let's do the union of a set with itself. Let's say that this is A and this is B. So let me do A union A. I have what? 1, 1, 2, union 1, 1, 2. And so here I want 1, 1, 2. And so when you do the union for each element in the union, you put the maximum of the two. In the other case that we discarded, I was putting the sum. So if when you do the union, you put the maximum. When you do the intersection, you put what? The intersection. The minimum. Very good. And so you see, all this makes sense. Right? All right, so let's take your favorite programming language. Are there set, multiset, Cartesian product? There are certainly libraries, right? Here, I took one for sets in Ruby. If I have the network, I'll just show you how it is. Here, look at the first line. A collection of unordered, there is no order, and no duplicates. Which is exactly what we said a second ago, right? So which kind of operation we can expect there? Let's see. Let's look at this one. You see it? This is a proper subset. So this is the one that we denote with the arc, the equal, and the cross. And if you look at this one, this is the subset. Subsets means can be the same or can be properly contained. So now, why we study 250? If you look at this one, whoever wrote this one assume that you know what means a subset. He's not going to tell you there what means a subset. And if you don't know what means subset and you try to use that one, probably you run in trouble. So here we have this separation. On one side, we study concepts in the abstract. And then, if you have to write code, you can find a library where those abstract concepts are translated in a programming language. Here is not telling you how this set is represented. If you have to write this library for your favorite programming language, how would you represent a set? No. Which instructions, which structure of your programming language? Let's say that we do this in C or C++. What would be a set? Well, a set has to be a container, right? Where you put elements. So, what are the containers? You could use an array. Is an array enough or you need more? No, I'm talking about the representation. I'm sorry?
Why don't you need a 2D array or a multi-dimensional array?
So why one dimension is not enough?
You're listing one would be okay.
Yeah?
So no one's could be sets.
Say it again?
So no one's could be sets.
No. They are all the same type. Yes?
Can we change this to that
Fundamentally change the question.
Yeah, because if you add to a set, then you want to make it something like
You could use a linked list. The simplest probably is an array, but you also needed to say what are the elements.
Yeah.
Because an array has a fixed size, like 100. But what if you put only 3 elements in the set? So you have to say the first 3 elements are elements in the set. The first 3 is long. And the rest is garbage. Right? And so if you have this one, then how do you define an operation like union and intersection? Right, you make another array for union. What do you do? Union A, B, you copy the first array in the result, and then you go over all the elements of the other one that are not yet there. If are not yet there, you just add it and make the array bigger. Right?
We got to check which array was bigger so that you didn't have to go through each element of the bigger one.
All right, you can optimize, but this comes later. But yes. Now, this may not be a great idea because you have to go over all the elements many times. So at some point you may learn about the trees and red, black trees, and sometimes these are a good way to implement sets. But basically you have the concept, right? So I don't know how it's implemented here and how efficient it is. We can look at other operation. I'm sure that there is something like union and intersection. So let me look for intersection. Okay. Intersection is this ampersand. This is intersection. And plus is union. All right, and you also have this difference with minus. So you see how the concept that we learned here, you find them in a programming language? What about the tuples? How would you implement the tuples in your favorite programming language? I'm sorry?
Just Python that already has them.
Which language already have them? Python. What in your favorite programming language? Favorite C++. Is a joke. C++.
You do have to use one of those since order matters.
Yes, the order matters. And linked list it wouldn't be an array wouldn't be good because in an array all the elements have to be the same type. But in a tuple, the first element can be a number, like the ID of a student, the second can be a name, the third can be a real, which is the GPA, and so on. The third one can be your address or whatever. This is how you make tuples. Say that again? Fantastic. Structure or class is already there. A class or structure is a tuple where the elements are named instead of having just position first, second, third. Right? So all a modern object-oriented language, the tuple is a key. All right, just to play a little bit with these ideas. Let's see at the homework. We look at the first. Let's see the second part. All right. So here you have the first problem. With that E, I represent all the even integers. Integers go from minus infinity to infinity. So the even integers contain dot 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 negative 4, negative 2, 0, 2, 4, dot dot dot. So if you do the intersection, union, or symmetric difference, right, which of the following is final? Symmetric difference. Why union and intersection wouldn't work? Remain itself, right? And of course it's infinite. Very good. I gave it away, right? All right, that's all. Here there is a definition for one set. What is P? What are the elements of P? Who wants to tell me a few elements of P? All right, so you write the elements of P and you decide which of those conditions is true, right? All right, I don't want to give away all of them. I just want to point you in the right direction. What is this one? This one here somehow is solving an equation where there are sets. Right? Can you try to solve an equation where there are sets and see how easy or difficult it is? So before I gave you two sets, A and B, and I asked you to compute, say, the union or the intersection, right? So now, let me give you a set A. I still keep a 1, 2, 3. And now I say A union B is equal 1, 2, 3, 4. Yes? Sorry? So how do you solve this for B? Basically, what B has to be in order to get the vector? Yes? 4. So someone says 4. This is the solution of the equation. Are there any other solutions? All right, so another solution would be 1, 4. Right? Or 2, 4. Or 1, 2, 4. And so there are many solutions, right? And so, by reasoning, we can solve simple equations with sets. And so, the other problem is solve an equation so we see whether or some condition on the equations. All right, there is one on power sets. Should be pretty easy. And then there is one with multisets, where these multisets are the set of the letters banana and Panama. You see there are repetitions there. So we can put the repetition in the multiset, and then you do operations like union, intersection, and stuff. So here, since you haven't done homework yet, there is an example of a question and the kind of answer that should be okay. Should we try to do it? We have two sets which are a little nasty because these are sets where you have elements and pairs of elements. So it's a little ugly, but it's going to test your understanding. And so I do the Cartesian product, and then I'm asking you whether something is there or not. So one way to do this one is, let's start to write the element of the Cartesian product. Why don't you try on your piece of paper to figure out what is that A cross B or C? So you get the hang of what is there, you don't have to write all the elements. By the way, how many elements are there? 9. Not a big deal, but you don't have to write all 9. After you write a few, you should get the hang of what is there. So is a 2A in C? No. Why not? In order to be there, you should find the 2 in A and a small a in B. But in big A there is no 2. So 2A cannot be there. You agree? Is a 3A there?
Yes.
Yes. Why? Because 3 is in A and small a is in B. And so you have the pair there. Alright? And so this is the kind of explanation that certainly will give you full credit for the problem and show that you understand. Yes?
So, for let's say you have the element of C that's like 1 and 3A.
Yes.
Does 3A maintain its own parentheses? Like
Yes.
how does that bubble?
Yes. So this will be a pair where you have 2 slots. The first one will be 1. And the second will be a pair, 3A, which has 2 slots, and the first is 3 and the second is 8. Fantastic. So with this one, we close this section. And I realized that I gave you the break after half an hour rather than an hour because I fell asleep for a second and no one woke me up. So don't be shy. If I fall asleep, please say, hey, wake up. All right, so we start to catch up a little. So we talk about functions. When we talk about function, a function typically is not thought as a discrete structure. It's not. The fact is that when we have discrete structures, this discrete structure consists of elements and a function that manipulates the element. For example, union and intersection are functions that take sets and produce sets. Right? And so now we want to spend a little bit of time understanding functions and their properties. Later in this lecture we have some fun because there are some programming languages that the only thing you have in the language is a function. They don't have anything else. And we will write some programs in these languages. And actually writing this program will be much shorter than the languages you are familiar with. Even if you have so little, only function. There is no assignment, there is no for, there is no while, there are no classes. So the only thing you have are functions. And the programs are much shorter and much faster to write. A little bit more detail. All right, so what is a function? In order to talk about the function, I have to talk about the pieces. And the 2 key pieces are 2 sets. One set I call domain of the function, and the other set I call codomain of the function. And so the function makes an association. Each element of the domain is associated to one element of the codomain. Right? So, if the domain is the set of students in this class, and the codomain is the set of chairs in this class, I can have a function that pick a student and associate it to the chair where he or she is sitting. This is a function. How do you call this function? My chair. Right? Very good. So here we have a notation. The function is f colon a arrow b. Arrow, of course, is overloaded. In logic, arrow meant something completely different. So don't be confused. Here, a and b are set. In logic, a and b were propositions. The function has a name, f. We could also have a function without a name. In programming languages, there are f. And how do we write it? We write f of x equal y, meaning that x is associated to y. So what's your name? Jimmy. So the function that associated Jimmy to his chair will be f of Jimmy, and then if the chair has a number or something, will be the number or the identification of that chair. F of Jimmy will be equal to that chair. Alright? Let's see some other example. The name of a student. What is the domain? The set of all students. What is the codomain? The set of all names. Parent of a student. This is not a function. Why is not a function? Right, because people have two parents, right? Now there is cloning, but they don't do it yet with humans. So this is still a good example. If you look at there, the first line, it said associated to each element of x, to each element x of A, exactly one element of y. Exactly one. No more, no less. If you don't have an element, it's not a function. If you have more than one element, it's not a function. Exactly one. Yes?
This definition in multiple elements in A map to a single element of B.
Yes, we are going to see it in a second. Yes. All right. So, parent of a student is not a function because we have two parents. Father of a student is a function. Mother of a student is a function. But parent is too bad. All right. What about x squared? The function that maps x to x squared is a function. Yeah. What are the function that takes an element and returns the square root of the element? Is a function? Right. We have to be careful because if the domain has negative numbers, maybe there is no square root of a negative number unless we start to talk about the complex. So, but if the codomain is the integer, what is the square root of 4? 2 or? Right, a negative 2, right? So again, here you have to be very careful. So here, I don't have a good answer to that question mark. The good answer is depends. Right, it depends on what is the domain, what is the codomain, and then maybe we have a function, maybe we don't. Alright, so here we have some concepts, but first look at this one. This is a function, right? What is the domain? X. The codomain? Y. So, Can we really claim that it's a function? Is it really true that for each element here there is exactly one here that corresponds?
Yeah.
Correct answer is yes. Is there a problem that here we have two that go here? Why not? Because if I take this element, there is exactly one that corresponds. Yes. What is it? C. And if I take this one, there is exactly one. Yes. Fantastic. Now, no one takes A because it stinks. Is this a function? Yes. According to the definition, for each element here, there is exactly one here that corresponds. And so it's a function. How could we change this one so it's not a function? How can we screw it up? Say that again?
F2 equal B.
Right. It has an arrow from 2 to C and an arrow from 2 to D. What would we violate? The exactly one. Because here we have 2. Can we screw it up in another way?
If there was a blue.
Right. If we take 3 and we don't have any arrow, there is not exactly 1. There are 0. Yes?
So are A and B part of the codomain? Is this the part of Y?
Yes, this is the codomain. Now, we could have another codomain where we take A away. This is almost the same function. For what really matters is the same function, but the codomain here is different. All right? So we have names for the various species. So if f of x is a y, we say that y is the image of x, and x is the pre-image of y. So what is the image of 3? C. What is the pre-image of C? 3 or 2. So we say that 2 is a pre-image and 3 is a pre-image. Some authors don't like this. So they talk only about sets. You take sets on one side and sets on the other. This author takes elements on one side and elements on the other. The concept is very, very similar. Here now we will have the set of C, and what is the pre-image of the set C? The set 2 and 3, right? What is the pre-image of the set C and A? Still 2 and 3, the set 2 and 3, right? And so we have this notion of image and pre-image. And we do it for elements and we do it for sets. And if we look at other books around, there are a bunch available on the website. You can go to Wikipedia, you can have a book yourself. That book may be like the author, where he mostly talks about elements, or maybe he just talks about sets. That's perfectly fine. When you understand one, the other one is automatic. Right? So if you take a set in X here, the image of all the set is called the range of that set. So the image of all X is called the range of the function. Range of the function. Range, you also use it in the normal English sense. So if you have a function that at each moment of the day or each hour of the day measures the temperature in July, how do you call the set of all the values? The range of the temperature. When you say that the range is 60 to 80, means that at some time the temperature was between there. That value was taken. Sounds good? All right, let's look at some functions and let's talk about them, particularly in a reference to programming languages. Floor, ceiling, truncate, round, These are functions that probably are available in your programming language. In your programming language, if you assign a real number to an integer number, a float to an int, or a double to an int, does it complain or not? I'm sorry? Probably complains. You have to cast it. So you put between parentheses int 3.14 and you call it cast. And what it's doing? Typically floor. Typically floor. So what is the floor of a number? Is the largest integer less than or equal to that number? So if you have a 3.14, what is the floor of 3.14? 3. If you have a 3, what is the floor of 3? 3. If you have negative 2.9, what is the floor? Negative 3. Right? So this is typically when you cast, you get the floor. What is the ceiling? Let me represent the numbers here on an axis where you have 0, here you have 1, 2, negative 1, negative 2, and so on. So if you pick a number here, what is the floor? The integer closest to the left. And what is the ceiling? The integer closest to the right. If you pick an integer, the floor and the ceiling of that integer are the integer itself. Right? And so floor is what the typically programming languages do. If you want ceiling, what do? You have to be careful because one idea is to take the floor and add 1. Right? But it doesn't work perfectly all the time. What is a truncate? Truncate, in most languages, for numbers greater than 0 is like floor. And for number less than 0 is ceiling. You have to understand the concept and you have to read the documentation. And what is round? Round is the closest integer. So if the decimal part is up to excluded 0.5, you take the floor. If it is 0.5 or more, you take the ceiling. And so here you get the smallest mistake when you go from a float to. All right? The graph of a function. You are probably familiar with the graph of a function, right? If I have a function, let me write a function here. Typically, we represent a function, we have the two axes. Yes, thank you. And the function is something like this, right? What is the graph? You may remember this from your study before. It's the set of all these points, right? This is the graph. Yeah? All right, so we define it here. And you say, if you have a function from A to B, the graph of f is what? Is a set of pairs, x, f of x, which is the one that I showed before, where x is in A. So suppose that my function is x squared. I have this function. Oh, sorry. function square that goes from the natural to the natural, right? What is the graph of this function? Who wants to tell me the graph of this function? First we have pairs, right? Then there will be one pair for each element of the domain. Exactly one. Why? Because for each element of the domain, there is exactly one element of the codomain that corresponds to it. Right? And so what are these elements? 0, 0, 1, 1, 2, 4, 3, 9, and so on. This is the graph of a function. Quite so good? All right. So I don't really want to overload you with a lot of concepts. We have all the concepts about sets, and we have all this concept about function. So I will stop at this here, and I will play a little bit. All right? So we make the lecture a little bit lighter. And the idea is to use functions for programming. It would be fun. So the scientists want to know how smart are animals, right? Monkeys in particular, because monkeys are smart. And so, we do this experiment in the room, touch a string with a banana at the bottom, let the monkey in. Of course, the monkey loves banana. And goes there, catch the banana, and eat. They do this for a couple of days. Monkey is very happy to come in the room and get the banana, but they play a nasty trick. This string from the ceiling all of a sudden is short. And the monkey goes there, right, the banana and can't. But there is a box in a corner of the room. So the monkey is very smart. Pushes the box under the banana, jumps on the box, and now can reach it, right? Incredibly smart. Why? Because the monkey is afraid that someone will get the banana. So the idea of getting away rather than staying there and protecting it really needs a very large brain to do that. And so now knows the trick, does it every day, run there, get it, and the scientist is nastier, so makes the string even shorter. And I don't see it here. And the monkey put the box there, but it can't. But in a corner there is a stick. Pretend that this is a stick. The stick is there. There is a stick. Now he's on top of the box and has the stick and still can catch the banana. Right? So, what I want you to do is to be the monkey, and your box and your stick are functions, and you have to catch some banana, and you have to put these functions together so that you get a banana. And this is a very creative process, exactly like the process for the monkey to get the banana. So let me tell you what are your functions. Let me make this a little bit bigger. All right. The first function is sec. Sec takes a natural number and will give you a list of natural numbers. So the domain are the natural numbers 0, 1, 2, 3, 4. And the codomain is the list of natural numbers. And if you give the number n, we give you 0, 1, 2, 3, up to n. You with me? So in particular, sec of 0 is the list 0. Sec of 1 is the list 0, 1. Sec of 2 is the list 0, 1, 2, and so on. You with me? This This takes an element, can be anything you want, and a list of elements, can be anything you want, and we give you what? A list of pairs, tuples, pairs, where the first is A, always A, and the second is the element of the list. So, let me make an example. If I have this, and here I pick a square, we do with numbers, but can be anything. And this is the list 3, 7, 2. What is this one? This will be the list of pairs square 3, square 7, square 2. You with me? Then you have map. Map takes a function and a list, and we give you the list where the function is applied to all these. So let me make an example of this so you understand the behavior. If you have a map double and you have the list 1, 2, 3, or square, because I had square before, what is the result with double? 2, 4, 6. Alright? And if it was square, what would be the result? 1, 4, 9. Alright? And then I have normal functions. Add takes a pair, x and y, and computes the addition. And you have multiplication, division, and everything else. Tail, I don't know how many people know about sequence, but the tail is everything except the first element. So here if you have b1, b2, bn, you get b2, bn. Alright? So now, I want to compute this one. 1, 2, 3, 4, 5. How do I do this? I'm sorry?
The tail is x equals 5.
Very good. Tail of sec of 5. How do you do the second one? Someone else. So you don't have double. You don't have double. These are the functions. Because if you have double, you just have a function. My favorite function in the world that will give you 0, 2, 4, 6, 8. These are your functions.
So instead of so the second one.
All right. So should I try to write it here?
So instead of, because we have multiplication and subtraction.
Yes.
So we have multiplication the second one.
So here I would have a sec of what? Sec of 4. Right. Sec of 4 is giving me what? 0, 1, 2, 3, 4. So now what do I do?
Math
We don't have multiply by 2. I only have this.
You can't partially
I have this. I don't know what the partial evaluation is. Yes?
math add x and x.
You are close, but you are not there yet. Now you do a dist 2, right? So if you do a dist 2, so sec 4 is 0, 1, 2, 3, 4. Now you do a dist 2. Yes, I switch camera, but you may want to see that one, so I need... now if you have a dist 2 of sec 4, you have what? 2, 0 pair, 2, 1 pair, 2, 4 pair. Yeah? And now what do you do? map multiply. Map multiply, and so 2 times 0 is 0, 2 times 1 is 2, 2 times 4 is 8. All right? So, I stop here, but for your pleasure, you can compute this one here. 5, 4, 3, 2, 1. All right, have a nice weekend.